Image quality and characteristics. This is chapter 9 from the Johnston and Faber book, Essentials of Radiographic Physics and Imaging. A quality radiographic image must have two things. It needs to show the anatomic area of interest for that exam, and it also needs to have information that is well visualized for diagnosis. The process of creating the latent image is by differential absorption, which we learned in last week's chapter. And then once that digital image has been acquired, it must be processed before displayed on a computer monitor, which is the manifest image. The visibility of the recorded detail refers to the brightness and the contrast of the image. The accuracy of the structural lines, which is the sharpness of the image, is achieved by maximizing spatial resolution. So you want to increase the spatial resolution, and then by decreasing the distortion. Visibility of the anatomic tissue is achieved by the proper balance of image brightness or density and contrast. The brightness is the amount of luminance, which is the light emission of a display monitor. The brightness level can be altered when displayed on a computer monitor. With brightness, we are going to change the brightness on an image with window leveling. So window leveling will go from top to bottom. So you'll move your mouse in a top to bottom style and it will get brighter and darker. To window width, which would be to alter the contrast of the image, you would take your mouse and you would go side to side, right to left, and it would change the contrast of the image. If you want to go from corner to corner, either corner to the other corner, you can change window level and window width at the same time. So again, the brightness is controlled by the window leveling and the contrast is controlled by the window width. This radiograph here of the knee does show sufficient brightness. So it does visualize the anatomic structures of interest that we're looking for on the knee. A radiograph that is too light has excessive brightness to visualize the structures of the anatomic part. And you can see here when you're looking at these two images, the image to the left has too much brightness. So it has excessive brightness. So we're not really able to see the structures that we want to see in the knee. The image to the right is too dark and it has insufficient brightness. So we're not able to visualize the structures of the anatomic part in the knee because it's too dark. So the one to the left is a radiograph with excessive brightness. The one to the right is a radiograph with insufficient brightness. And brightness can be altered with post-processing, like we said before. With the window leveling, you can alter the brightness of the image. The radiographer must evaluate the overall brightness on the image to determine whether it is sufficient to visualize the anatomic area of interest. He or she then decides whether the radiograph is diagnostic or unacceptable. In order to evaluate other attributes of the radiographic quality, such as the contrast and the sharpness, the image must have sufficient brightness to visualize the anatomic area of interest. We can post-process, and we are able to change the brightness and the contrast of an image, but sometimes the image is just too light or too dark to where we're not able to post-process and change any of these factors. Digital image processing can compensate for exposure errors and maintain brightness. So this is what they're talking about with the post-processing, but sometimes it's too light or too dark and we're not able to actually post-process. The underexposure may result in increased quantum noise, and then extreme overexposure may result in saturation. Here we're looking at two radiographs of the thumb. In figure A, you can see the radiograph has sufficient exposure. We're able to see bony detail. We can see tissue. And then in figure B, the radiograph is extremely overexposed and the quality is severely degraded. And because it is so severely overexposed, we are not able to use window width or window level to correct this. So it would need to be repeated. The EI, or exposure indicator, provides a numeric value indicating the level of radiation exposure to the digital image receptor. The industry is working towards standardization of the exposure indicator. The radiographer should evaluate the EI value along with the quality of the image before determining whether a repeat image is warranted. So every department you work in will have different EI standards. So just depending on if they use GE or Siemens or what operating system they use to make a digital image, but they'll have different EIs that are within the normal range. So you'll need to know what range your EI is in. A lot of our digital image processing will actually show the EI. It'll show it up as green if it's okay and if it's within range. If it's out of range, it'll show up as red. So then you'll know, if you look at the image and you see, not really sure if this is diagnostic quality, and then you look at the EI and it's in the red range, then you know that you probably need to repeat that image. So it'll be a diagnostic quality for the radiologist. A wide dynamic range is only useful if the displayed image brightness can be optimized for human perception. Changing the window level on the display monitor allows the image brightness to be increased or decreased throughout the entire range of densities. Shown in this figure here, this is window leveling. So changing the window level increases or decreases the image brightness throughout the range of densities recorded in the image. So if you look at this figure here, it will show subject density and image brightness. So your subject density will be on the left. So it'll be here, and then you have your image brightness over here. So it's showing you the air, the fat, the water, the muscle, and the bone, and how much white and black range of brightness the image will have depending on what it has to go through, what types of densities it has to go through. With brightness, moving the window level up to a high pixel value increases overall brightness on the display monitor, increasing visibility of the darker anatomic regions. So if you have a dark image, you want to window level. So you want to move your cursor up so it gets brighter. Moving the window level down to a low pixel value is going to decrease the brightness, so it's going to become darker on the display monitor. This is going to increase the visibility of brighter anatomic regions. Assume that pixel values from 0 to 2048 are used to represent the full range of the digital image densities or brightness levels. So it goes from 0 all the way to 2048. So a high pixel value all the way at 2048 could represent a volume of tissue that attenuated fewer X-ray photons and is displayed as a decreased brightness level or increased density. Therefore, a low pixel value represents a volume of tissue that attenuates more X-ray photons, and it's going to be displayed as increased brightness or decreased density. The range of brightness levels is a result of the tissue's differential attenuation of the X-ray photons. Now, it'll depend on what type of tissue we're talking about. So an image that has sufficient brightness but no differences appears as a homogeneous object. This appearance indicates that the absorption characteristics of the object are equal. In this figure here, it's going to show homogeneous. It's a radiograph of a homogeneous object having no differences in density, and you can see it's all the same shades of gray. It's all the same color. There's no differences in the densities. There's no differences in the brightness. There's no contrast. So lack of contrast makes an object appear homogeneous. When the absorption characteristics of an object differ, the image has varying levels of brightness. The anatomic tissues are easily differentiated because of these differences in brightness. For example, contrast. Tissues that attenuate the X-ray beam equally are more difficult to visualize because the brightness levels are too similar to differentiate. In this figure here, it's showing differential absorption. This is an object with different absorption characteristics producing an image with varying densities. So you can see this is a clavicle here, and you can see in the clavicle, it's dark and light at this end, and then it's light all the way down the body and shaft, and then at the other end it's going to be dark. And that's because of this other object here that we have also x-rayed within the same display array, and so it's not able to concentrate on one bone or one object. And so now it's having to concentrate on two different objects, and there's a lot of differences in the tissues. There's a lot of differences in the brightness. Radiographic contrast is the combined result of multiple factors associated with the anatomic structure, the quality of the radiation, the capabilities of the image receptor, and in digital imaging, the computer processing and display. Subject contrast refers to the absorption characteristics of the anatomic tissue, radiographed, and the quality of the X-ray beam. Differences in the tissue thickness, the tissue density, and effective atomic number contribute to the subject contrast. The level of radiographic contrast desired in an image is determined by the composition of the anatomic tissue that's being radiographed and the amount of information needed to visualize the tissue for an accurate diagnosis. Evaluating radiographic quality in terms of contrast is more subjective than evaluating brightness. The chest is composed of tissues that vary greatly in X-ray lucency, such as the air-filled lungs, the heart, and the bony thorax. The anatomic region creates high subject contrast because the tissues attenuate the X-ray beam very differently compared with the abdomen for the same beam quality. Looking at the figure on the left, where it says bone, fat, and air, this is showing high subject contrast. So higher contrast resulting from great differences in radiation absorption for tissues that have greater variation in composition. So bone is going to appear white on the image. Fat will appear gray. Air will appear black. So if you look at the image of the chest x-ray, this is high subject contrast. The chest is an area of high subject contrast because there is great variation in tissue composition. Because we have all of those. We have bone, fat, and air all inside of the thorax. And so that is going to give us that higher contrast, which are different shades of gray. The abdomen is composed of tissues that attenuate the X-ray beam similarly and is considered to be a region of low subject contrast. The brightness levels representing the organs in the abdomen are more similar to each other. Therefore, it is difficult to distinguish the stomach from the kidneys. If you look at the figure on the left, where it says muscle, water, fat, you can see that the shades of gray are almost the same shades. You know, one's a little bit lighter than the other, but basically throughout the abdomen, they're all shades of gray, because what are you looking at in the abdomen? You're looking just at different tissues, right? So this is considered lower contrast. So the lower contrast resulting from fewer differences in radiation absorption for tissues that are more similarly composed. If you look at the abdomen x-ray, the abdomen is an area of low subject contrast because it is made up of similar tissues. So unlike the chest x-ray that we saw, where they have bone, fat, and air, it's a little bit different because that was high contrast. You could see a lot of differences. This one has muscle, water, and fat. So it's just a lot of shades of gray. So this would be low contrast. The quality of the X-ray beam also affects its attenuation in tissues, which alters the subject contrast. Increasing the penetrating power of the X-ray beam decreases attenuation, reduces absorption, and increases X-ray transmission, resulting in fewer differences in brightness levels in the radiographic image. Decreasing the penetrating power of the X-ray beam is going to increase attenuation and absorption, and decrease the transmission, resulting in greater differences in the brightness levels in the radiographic image. So basically what this is saying is, if we give the X-ray beam more penetrability, which means it's going to get through all the tissue quicker, it's going to have less time to attenuate, less time to absorb, and more time to actually transmit and hit the image receptor, giving us the digital image. So we want that. We want to increase our penetrating power. So we always want to keep our KV high and our mass low. That's the best for patient exposure, and it's also the best for a digital image. Shown in the left figure is going to show you high contrast. It's a short scale, and it's an image showing fewer gray tones and greater differences between the individual densities. And then on the right side, you have low contrast, which is long scale, and it's an image showing lots of gray and little difference between individual densities. In digital imaging, the number of different shades of gray that can be stored and displayed by a computer system is termed the grayscale. The contrast resolution of the imaging system determines the level of visibility of the small objects having similar densities or similar shades of gray. The depth of the pixel is determined by bit depth, which affects the number of shades of gray available for the image. Increasing the number of shades of gray increases the contrast resolution within the image. An image with increased contrast resolution is going to increase the visibility of recorded detail and the ability to distinguish among small anatomic areas of interest. Because of the digital image, we can display grayscale levels ranging from black to white. The display monitor can vary the range or number of brightness levels visible on the image to show all of the anatomy. Remember, window width adjusts the radiographic contrast. So by taking your cursor and going from left to right or from right to left, you're able to window width your image, and you can change the contrast of your image. Radiograph A is showing high contrast, and radiograph B is showing low contrast. When the entire range of brightness levels are displayed, it's called the wide window width. The image has lower contrast with wide window width, or more shades of gray. When a smaller range of brightness levels are displayed, which is called a narrow window width, the image has higher contrast or fewer shades of gray. The center or midpoint of the window level and window width determines the brightness and the contrast of the displayed image. In this figure here, the level or center of the window and the window width changes the visual display of the digital image. So going from up and down, let's see if I can get the pointer to show up. Okay. So going up and down, like I said before, that is the window level, and we are changing the brightness of the image. Going left to right, that is the window width, and we are changing the contrast of the image. Changing the window level for a chest x-ray varies the visibility of the anatomic detail or the contrast for both low and high density areas. So if you look at this picture here, the chest x-ray to the left, this has good contrast in a lower range of pixel values. This is the low window. And then the x-ray to the right, this is the high window. This has good contrast in higher range of pixel values. So this will need to be window leveled and window width, and you can go corner to corner to do that. A digital image is composed of discrete information in the form of pixels that display various shades of gray. The size of the pixel is measured in microns. 100 microns equals 0.1 millimeters. The greater the number of pixels in a matrix image, the smaller their size. An image consisting of a greater number of pixels per unit area or pixel density provides improved spatial resolution. In addition to its size, the pixel spacing or distance measured from the center of a pixel to an adjacent pixel determines the pixel pitch. A major determinant of spatial resolution of digital images is the pixel size and its spacing. And if you can look at this image here, this is the pixel pitch. This is the pixel spacing or the distance measured from the center of a pixel to an adjacent pixel, and it will affect the spatial resolution of the digital image. The greater number of pixels in a matrix image, the smaller their size. An image consisting of a greater number of pixels per unit area or pixel density provides improved spatial resolution. So now we're going to look at image A, B, and C. In image A, this image has 20 pixels per centimeter. Therefore, the pixel size is larger and the spatial resolution is poor. In image B, we have 40 pixels per centimeter. And then image C, we have 100 pixels per centimeter, and therefore the pixel size is smaller than that in images A and B, and the spatial resolution is improved. So if you were to pick one of these images to send to the radiologist, which one would it be? I would pick image C, the one with the most spatial resolution. That's more of a diagnostic quality image to send to the radiologist. There is a relationship among pixel size, field of view, which is the FOV. The field of view is the dimensions of an anatomic area, and the matrix size, and it's all demonstrated in this formula. So if we're looking for pixel size, it will be field of view divided by the matrix size. This relationship demonstrates that if the field of view is increased for a fixed matrix size, then the pixel size is also increased, which is a direct relationship. So that's directly proportional. However, if the matrix size is increased for a fixed FOV, then the pixel size is decreased, and that's an inverse relationship or inversely proportional. So if we have a field of view that is 17 inches, so that's your field of view. And then the matrix size, so we'll put an M for matrix, is 1024. And we need to find the pixel size. So first we need to convert 17 inches into millimeters. So the field of view will be 431.8 millimeters. And then we need to divide that by your matrix size, which is 1024. And that will equal 0.42 millimeter pixel size. Sorry, this thing does not allow me to write very clearly, but you get it. Okay, so for the field of view, it is 17 inches. We converted that to millimeters, which is 431.8 millimeters. The matrix size is 1024. We divided 431.8 millimeters divided by 1024, and that equaled 0.42 millimeter pixel size. Now, if we were to decrease the field of view to 12 inches, let's see what that would be. So here's our field of view, which is 12 inches. Okay. We will need to convert that to millimeters. So converting that to millimeters would be 304.8 millimeters. And then we need to find out the pixel size. So the matrix size is 1024. Again, we've got our matrix 1024. And so all we're doing here is we are taking our field of view from 17 inches to 12. So we need to divide 304.8 millimeters divided by 1024, and that's going to equal your new pixel size, which is 0.30 millimeter pixel size. Decreasing the field of view for a given matrix size will decrease the size of the pixels and increase your spatial resolution. So spatial resolution is determined by the size of the pixels and the spacing between each, which is the pitch. So if we have more pixels, that is going to increase your spatial resolution. So going back to the last slide, how do we convert inches to millimeters? You're going to multiply the length value of inches by 25.4 millimeters. So for instance, in the last slide, we had 17 inches and we needed to convert that to millimeters. So we took 17 multiply it by 25.4 millimeters, and that came up to 431.8 millimeters. And that's what we used in our last equation, okay? Now, this equation is a little bit different. So our last equation, we changed the field of view size. So we changed the field of view from the first equation to the second. And on this one, we're going to be changing our matrix size instead. So I'm going to pick purple this time. So our field of view is the same as last time. So it's going to be 431.8 millimeters because I've already converted it. We're going to divide that by the matrix size, which is 1024. And that will give us our pixel size of 0.42. So this is millimeters, and that's our pixel size. So now we're going to go down here, and instead of changing, like before we changed our field of view from 17 inches down to 12 inches, this time we're doing pixel size and matrix size. So we're changing our matrix size. So for the second part, we're going to keep our field of view the same. So it's going to stay 431.8 millimeters. And we're going to divide this by our new matrix size, which is 2048. And that is going to give us our new pixel size of 0.21. 0.21 millimeter pixel size. Okay. Increasing the matrix size for a given field of view will decrease the size of the pixels and increase spatial resolution. So this one here is increasing your spatial resolution. The quality of a radiographic image depends on both the visibility and the accuracy of the anatomical structural lines recorded, which is the sharpness. And to produce a quality radiograph, the anatomic details must be recorded accurately and with the greatest amount of sharpness. Spatial resolution refers to the smallest object that can be detected in an image, and it's the term used in digital imaging. Resolution is the ability of the imaging system to resolve or distinguish between two adjacent structures. Resolution can be expressed in the unit of line pairs per millimeter, so LP/millimeter. A resolution test pattern is a device used to record and measure line pairs. The greater the number of line pairs per millimeter resolved, the greater the resolution. So you can see the line pairs measurement here in this image. It's the resolution test pattern, and it measures and records line pairs per millimeter. Resolution is the ability of the imaging system to resolve or distinguish between two adjacent structures, meaning they're right next to each other. Resolution can be expressed in the unit of line pairs per millimeter, which is written LP/mm. An imaging system that can resolve fewer line pairs with 1 millimeter is said to have decreased sharpness. The ability to discern small changes in spatial resolution when viewing a radiographic image is dependent on the visual acuity and the distance of the viewer. Resolution is the ability of the imaging system to resolve or distinguish between two adjacent structures. So we know resolution can be expressed in the unit of line pairs per millimeter, which is the LP/mm that I wrote. In this figure, it is showing the line pairs per millimeter, 5 line pairs in the space of 1 millimeter. It is 5 LP/mm. A line pair includes a line and a space. So if 5 LP/mm are visualized, a line pair measures 0.2 millimeters and each line measures 0.1 millimeters. So if you look at this figure here, you can see that the line pair, or LP, equals 0.2 millimeters. So we have that here. This is the line pair. Okay. We have the airspace. Then we have a lead strip. Airspace, lead strip. Keeps going. One of these is a line, and it is 0.1 millimeters. 2 of these is a line pair, and it is 0.2 millimeters. Spaces in between is 0.1 millimeters. So again, a line pair is going to include a line and a space. So if each line pair includes a line and a space, then if we have 5 LP/mm that are visualized, a line pair is going to measure 0.2 millimeters, and then each line is going to measure 0.1 millimeters for a total of 5. Spatial frequency is defined by the unit of line pairs per millimeter. Small objects have higher spatial frequency and large objects have lower spatial frequency. Increasing the number of LP/mm resolved in the imaging system results in improved spatial resolution. So here you can see this is a line, and each line is 10 millimeters. So if we have 2, then one line pair is 20 millimeters. And these are all equal interspaces. Over here, we have 5 and 5. And that's one line pair that equals to 10 millimeters. Here's some smaller lines. This is one line pair, and it's equal to 2 millimeters because each line is 1. And then so forth, it goes down. So it'll show the spatial frequency. It shows 0.05 all the way up to 10 line pairs per millimeter of spatial frequency. So it starts down here. This is 0.1 and goes all the way up to 10 each, adding to 20 millimeters for that line pair. If unsharpness is increased, the visibility of small anatomic detail is compromised. So an increase in the amount of unsharpness on an image decreases the contrast of small anatomic structures, and we're not able to visualize the structural lines. The spreading of the structural lines with increased unsharpness decreases the differences in brightness or density between the structural lines of the area of interest and that background. As a result, the difference in brightness between the area of interest and the background becomes less, lower contrast, and the visibility of the anatomic structure is reduced, and it actually becomes a part of the background and we don't see the difference. This image here is showing unsharpness with image contrast. So increasing the amount of unsharpness is going to decrease the brightness or density difference, the contrast, between the area of interest and its surrounding background. So we want as little unsharpness as possible, because if you have a small amount of unsharpness, you can see there's a big difference here in brightness or density. Medium unsharpness, it's getting hard to tell where the object is. And then a lot of unsharpness, the object is actually blending in, starting to blend into the background. So with a tiny bit of unsharpness, you'll have 100% of relative contrast, which is what we want. Medium unsharpness, you'll have 50% of the relative contrast. Large unsharpness, you go all the way down to 20% of relative contrast. So you have lost 80% of the visibility of the anatomic detail, of the sharpness of the lines, the structures, all of that stuff. You've lost 80% of that. In MTF, or modulation transfer function, it is to measure the imaging system's ability to display the contrast of anatomic objects varying in size. So values range between 0 and 1.0. An imaging system that has a high MTF can display anatomic detail with improved visibility. Most digital systems, MTF measures much lower than 1.0. To find out an MTF, we want to divide the maximum intensity minus the minimum intensity over the maximum intensity plus the minimum intensity. And that would give us the modulation transfer function. Detective quantum efficiency, or DQE, is a measurement of the efficiency of an image receptor in converting the X-ray exposure it receives to a quality radiographic image. The higher the DQE of a system, the lower the radiation exposure to produce a quality image, thereby decreasing patient dose. So again, the image receptor with higher DQE requires less X-ray exposure to produce an image as compared to an IR with a low DQE. Some information is always lost during the process of image formation. Also, factors such as patient motion increase the amount of unsharpness recorded in the image. It is the radiographer's responsibility to minimize the amount of information lost by manipulating the factors that affect the sharpness of the recorded image. Diagnostic quality is achieved by maximizing the amount of spatial resolution or recorded detail and minimizing the amount of image distortion. So we want to maximize resolution and minimize image distortion. When the image is distorted, spatial resolution is reduced. The term size distortion or magnification refers to an increase in the image size of an object compared with its true actual size. Radiographic images of objects are always magnified in terms of the true object size. The source to image receptor distance, or the SID, and also the object to image receptor distance, the OID, play an important role in minimizing the amount of size distortion of the radiographic image. Misalignment of the central ray among these three factors, the tube, the part, and the IR, alters the shape of the part recorded. So looking at the images here, this is all shape distortion. So A is going to be no distortion. So A is the true actual size of the bone with maybe a little bit of magnification. B is foreshortened, which means it's shorter. And then C, elongated. It's a lot longer than the actual size of the bone. And this can all be from either the tube, the part, or the image receptor being misaligned. Scatter radiation can add unwanted exposure to the radiographic image as a result of the Compton interactions. So if we look here in this figure, scatter degrades or decreases the visibility of the anatomic structure. In A, you can see an image created with less scatter compared with image B. Image B looks very foggy, so image B was created with increased scatter. It is important to minimize the amount of quantum noise or quantum model on a radiographic image. Shown in this image here, we're looking at some quantum noise. In image A, an image was created using an appropriate X-ray exposure technique. And then in image B, image shows increased quantum noise as a result of the insufficient X-ray exposure to the IR. And you can see that in image B, you can see the graininess. It's very grainy. Right here, you can see all this graininess. Where in A, it's clear and there's no graininess in image A. A method of describing the strength of the radiation exposure or the signal in comparison to the amount of noise apparent in the digital image. Increasing the SNR means that the strength of the signal is high compared to that amount of noise. Increasing the SNR will improve the quality of the digital image. Increased noise will decrease the visibility of the anatomic details. So if you increase the SNR, it will increase the improved image quality, but it will also increase patient radiation exposure. If you decrease the SNR, it decreases the image quality, but it also decreases patient exposure. So it's kind of like the risk versus the benefit thing, where we kind of have to increase certain things to get a good image quality, and we just have to take the risk of giving the patient a little bit more X-ray exposure. So risk versus benefit. The benefit will be that we get a really good quality diagnostic image to send to the radiologist, and then the risk will be increased patient exposure. Shown in this figure is contrast to noise ratio, or CNR. In image A, it is an image of a contrast detail phantom showing an increased contrast to noise ratio. Phantom objects are more visible. And then in B, it is an image of contrast detail phantom showing a decreased contrast to noise ratio. The phantom objects are less visible, and you can see it's grainy, just like I showed you before. It's the graininess doesn't allow us to see the anatomic details. So a CNR is a method of describing the contrast resolution compared with the amount of noise apparent in a digital image. Increasing the CNR increases the visibility of anatomic details. So we want the CNR to be increased because that will increase the details, and that is what figure A is showing you, or image A. An artifact is any unwanted image on a radiograph. Artifacts are detrimental to radiographs because they can make visibility of anatomy, a pathologic condition, patient identification information, difficult or impossible to see. They decrease the overall quality of the radiographic image. Various methods are used to classify artifacts. So on this one, in this chest x-ray here, you see the necklace. So that is an image artifact, and it is radiopaque. So if the patient did have a tumor or something else hiding behind this pendant on the necklace, we wouldn't be able to see it because this pendant is radiopaque, so it's blocking whatever's behind it. So artifacts are detrimental because they are going to make anatomic information difficult or impossible to see, and there could be pathology hiding behind that. Always make sure when you're doing any kind of x-ray that you get any artifacts out of the way. So necklaces on a chest x-ray, bracelets on a wrist x-ray, earrings for skull and spine x-rays. So make sure you're always having your patients take off any unwanted artifacts. Digital image artifacts can be a result of errors during extraction of the latent image from the image receptor, inadequate IR eraser, or performance of the electronic detectors. So in figure A, we see bright lines in the shoulder right here. And that's a result of scratches on the imaging plate. In figure B, we see bright specks between the 4th and 5th metacarpals. So we see bright specks in this area here. And that's as a result of dirt on the image plate. So if you're using computed radiography where you have image plates, make sure that you are cleaning the screens properly with the screen cleaner that comes with it. And make sure they're being cleaned, regularly to get any dust or dirt or anything like that off of there so that it does not create a digital image artifact.